Drop a like and do share. Leave your comments and do not forget to subscribe for more videos.
Hi friends, welcome back to the course on Introduction to Material Science and Engineering offered by EdupediaWorld. Previous lecture we discussed about dislocations and deformations, the different strain fields which develop around a dislocation, and how a dislocation helps in deformation. Also we discussed how a dislocation moves through a crystal. Today's lecture, what we'll see is about slip systems. If you remember from the previous lecture, we discussed about slip planes. It was the plane along which the dislocation moves. We'll see these same thing in much more details in today's lecture. The idea is that there are certain crystallographic planes and direction along which the movement of dislocation is easy. So those are the preferable planes. There are certain planes which are preferable planes for dislocation motion, and even in those planes there are certain directions which are preferable for the dislocation to move. This set of planes and direction are together called as the slip system. So put together, dislocation motion is preferred along certain crystallographic planes which are known as slip plane, and in those slip plane along specific direction which are known as slip direction, and the combination of the slip plane and the slip direction is known as slip system. Okay, now the slip system for a particular metal depends on what is the crystal structure of that metal. So slip system is a property of the crystal structure, as we'll see in the next slide. So depending on the crystal structure, whether it is body centered cubic, face centered cubic or hexagonal, a specific set of planes will be the slip plane and a specific set of directions will be the slip direction. Now the very basic idea why a particular plane is a slip plane and why a particular direction is a slip direction is the ease with which the dislocations move in that plane and that direction. What provides the ease? The ease is defined by how much energy is required for the dislocation to move in that plane in that particular direction. So if the movement of a dislocation requires less energy in a particular plane, then it is said that the dislocation is easy to move in that plane. How do we require less energy? Less energy is required for closely packed planes. If the planes are very closely packed or the gap between atoms is negligible, that is the atoms are almost touching each other, then it is easier for the atoms to move past one another. So close packed planes are the preferred planes. They will be the slip planes, and even in the close packed planes, the close packed directions are the preferred direction. So what defines the slip system? The slip system will depend on the close packed plane and in that plane the close packed direction. So let us see the different slip systems for different crystal structure. To begin with, let's see the face centered cubic system. Just to remind you, the face centered cubic has atoms at the corners and at the face center. So there will be atoms at 8 corners and atoms at the 6 face centers. Okay, and the face centers, this will be the close packed planes. The atoms are touching each other along this plane. So what is this plane? This plane is basically 1 1 1 plane. So the family of planes, family of 111 plane will be the slip plane for face centered cubic, because the atoms are closely packed in that direction, in that plane rather. And even in that plane, this direction, that is the diagonal, the face diagonal, that will be 110, is the close packed direction, that is the atoms are touching each other in that direction. Therefore the slip direction for face centered cubic is 110 direction, or 1 bar 0 family of directions. Fine. Now the combination this and this gives rise to 12 systems. If you make all the possible combinations of 111 and plane and 1 bar 0 direction, you will get 12 slip systems for a face centered cubic system. Some example of FCC are copper, aluminium, nickel, silver, gold. For the body centered cubic, what do we have is that we have atoms at the 8 corners, atoms at the 8 corners, and an atom at the body center, right? So this touches all the 8 atoms, but there is no plane which is completely packed. There is a direction which is packed, that is the body diagonal, that is completely packed. Okay, so the body diagonal is basically 111 or bar 111, right? So this is the slip direction because it is the packed direction. But the most packed plane is the 110, then there is 211, and there is 321. For this combination we have 12 planes, this combination we have 12 planes, this combination we have 24 planes. Okay, therefore for BCC we have a net of 48 slip planes, slip systems rather. These are slip systems, number of slip system. But in this 48 slip system, none of them are as good as the slip systems of FCC, because FCC had the closest packed plane and the closest packed direction. Here we have the closest packed direction, but the planes are not the closest packed. This is the best packing that is available, 110, that is 110. So the basically this plane, right, this plane is the best packed plane, but that is not as good packing as there can be. Therefore these 12 slip systems are good slip systems, that is the dislocation can move over there, but it will require more energy than that would be required for the FCC slip systems. Fine. But they have a good number of slip systems. They have 48 slip systems which require a little more energy, but they let slip to happen. In the case of hexagonal closed packing, the closed packed plane is the basal plane. There we had in the base we had like something like this, 1 atom and 6 atoms surrounding it. This is the closed packed plane, and in the closed packed plane we had 2 bar 0 direction, that is the closed packed direction. But the catch here is the total number of slip systems that we can get out of it is only 3, right? Only 3 slip systems that we can get out of the most closest packed plane. And in addition to that, the secondary closest packed plane has 3 and 6, but these are not as effective, because they are not the most close packed planes. They are the close packed direction but not the most close packed planes. So FCC has very effective slip systems, BCC has relatively less effective slip systems but has more number of slip systems. HCP has good slip systems which are very less in number, only 3. I'll not go into the details of the idea which I'm about to tell next, but if you study the fundamentals of geometry, then you'll know that for slip to happen, for dislocation motion, for deformation to happen, what we need, this comes from the very fundamental of geometry and from stress strain relations, that we need a minimum of 5 slip systems and effective deformation to take place. Effective deformation. We need 5 slip system. Therefore, FCC can have very good deformation properties. It is easily malleable, it is easily ductile. BCC, though, do not have very effective slip systems but have a large number of slip systems, so they also show relatively good malleability and ductility. The problem comes with hexagonal closed packed because they only have 3 slip systems which are effective. So if you read about the details, then hexagonal closed packed systems, you will see that they are not very malleable or ductile materials, which comes as a great hindrance in like automotive industry. I'll give you an example. What happens is automotive industry mainly uses aluminium alloys now. Aluminium alloys, being the FCC kind, is easily malleable and ductile. Okay, but it has a density of around 2.7 gram per cc. Magnesium, on the other hand, has a density of 1.7 gram per cc, which is approximately reduction of 30%. But magnesium, being a hexagonal closed pack system, has only 3 effective slip systems. Therefore, it is not easily deformable. Therefore, it is quite difficult for magnesium to replace aluminium in the automotive industry, though a lot of research is going on to bring the effective number of slip to 5. Okay, there is something which I won't go into the details of, known as twins. In the case of magnesium, in addition to the 3 slip systems provided like this, 1.5 slip systems is provided by twins. That gives a total of 4.5 slip system. Now, in addition to that, for the lacking of 0.5 slip system, there are additional alloying elements added, and a lot of research is going to bring it to 5. If the ductility, if the malleability becomes good for magnesium, then a lot of automotive sector is going to transform from aluminium to magnesium, thereby reducing the weight, increasing the fuel efficiency, and that will be a big boost to the automotive industry. Fine. So this was basically to give you an idea that what a slip system is, what are the different types of slip systems for the different type of crystal structures, and this kind of gives you what is the importance, the practical relevance of slip system. Okay, next up, let's see the slipping in the case of a single crystal. Suppose we have a single crystal. Single crystal means throughout the crystal the orientation is same, right? Now, if this were a FCC crystal, then there would be an effective of 12 slip systems, right? And if a force is applied like this, then it's not necessary that one of the slip systems lies in this direction, falls along this direction. Suppose we find the component of force along all the 12 slip systems. This force will have a component along all the 12 slip systems, and suppose we find those components, and what we get is that this slip system has the most effective component along this direction, along this slip system. That is, this slip plane is and this slip direction is energetically the most favorable plane and direction, that is the most favorably positioned slip system for the deformation to take place, for dislocation movement to take place. Then dislocation motion will take place along this slip system. If on the other hand there were a slip system like, let's say like this, which was more effective, if there were a slip system along the direction of the force, then obviously maximum component of the force would be in this slip system itself. Therefore the dislocation movement then would take place in this direction, if this was the direction. The idea is that in a single crystal the dislocation motion will be same throughout the crystal, because there is no hindrance in the form of grain boundaries or anything. Throughout the whole specimen the direction of slip will be same. The direction of slip is not going to change anywhere. Therefore what happens in a single crystal, once the dislocation starts to move, once we provide sufficient amount of force for the initiation of dislocation motion, the dislocation will keep on moving and the deformation will take place. Therefore single crystals are easily deformable if there are dislocations present in them. If we have a crystal which is a perfect crystal, that is there is no dislocation present, then single crystals are very strong. But it is very difficult to have a single crystal without any dislocation, and the presence of dislocation brings down the strength of single crystals drastically. Thereby single crystals are quite soft in nature because there is no hindrance in form of grain boundaries or anything. On the other hand, in the case of polycrystal, what happens is that there is random crystallographic orientation in different grains, right? There are different grains and each grain will have a different crystallographic orientation. So let's suppose a force is applied like this. The favorable plane of slip system is this direction, let's say in this grain. In this grain, let's say it is this direction. So what is happening is the dislocation moves from here to here and then it gets blocked over here. So now the next for the dislocation to move from here to here, sufficient stress needs to develop over here such that either this dislocation which came here breaks through the grain boundary and travels in the next grain, or sufficient number of dislocations accumulate here so as to generate enough strain to generate new dislocations in the adjacent grain and let those dislocations move further. Right. So here what is happening is, since there is continuous change in the slip system due to the presence of grain boundaries, the dislocations are physically restricted. As a result, larger amount of stress will be required for the dislocation to move through the crystal. Thereby the strength of a polycrystal increases compared to that of a single crystal. Okay. Due to the physical constraint provided by the grain boundaries. That's the bottom line, that polycrystals are generally much more stronger than single crystal. Exception being single crystal do not have dislocations, then single crystal are the strongest known thing on earth. Okay. With this background, I will close today's lecture. This lecture was dedicated on slip and slip systems. We understood what slip system is, what slip plane is, what slip direction is. We saw the different slip systems for FCC, BCC, HCP. We discussed phenomena of slip on a single crystal, in a single crystal and in a polycrystal, and how the two are different, and how the idea that slip gives rise to deformation and how restriction of slip gives rise to an increase in strength. Those things were discussed in today's lecture. So with this, I will conclude today's lecture. Have a great day. Goodbye.